Hey guys, in this week's lab, you're going to be doing a cheerwine colorimetry. Don't confuse that word colorimetry with the word calorimetry, which deals with energy and specific heat. In colorimetry, we're going to use light and send through a sample. And what we're going to do with this is use your phone as a colorimeter, which is pretty cool. There'll be an app you will download from either your app or Play Store, and you're going to send light through a sample of cheerwine. Make sure you do take time to look over the lab handout. There is some very useful information in the pre-lab that you're going to need. And with that, we're going to go ahead and look at some of the specifics you'll be working with. So as we go ahead and prepare to get started, let's talk some about what colorimetry is. It's the process of where we find the concentration of an unknown solution using light or electromagnetic radiation. If you have not yet already started, you will be starting a unit where you're going to look at electromagnetic radiation. And electromagnetic radiation is more or less officially the name for light. What we're going to do is send light through a sample. We call that incident light. We compare it to the amount of light that comes out of the sample, and that is either called the light absorbed or transmitted. If a sample contains a high amount of solute, then more of the light will be absorbed because the solute particles are going to absorb light. If you were to take a flashlight and shine through an empty room, that light's going to go straight through because there's nothing there to absorb it. However, if you put a lot of people in that empty room and send that light through, then a smaller amount of that light will come through because the people have basically absorbed the light. So if a sample contains a high amount of solute, then most of the light is going to be absorbed and the amount transmitted is low. So you're going to see a lot of solute there, and in that case we would say that solution is concentrated since the solute concentration is very high. So there'd be a very low amount of light that comes through. If, on the other hand, the sample contains a small amount of solute, then more of the light is going to be transmitted. It will go through, and that would be a low absorbance. In that case, we would call this solution dilute. In this lab, one of the other things we're going to have to use is the dilution equation. With the dilution equation, what we're going to be doing is taking what is called a stock solution. The stock solution is one that we know the concentration of, and we're going to take that stock solution and we're going to make several different samples to run. This is going to allow us to get some colorimetric data to begin to create what we need to do as a Beer's Law plot. And so with that, we're going to take a known concentration and make several different samples that are smaller in concentration. And when we do that, we're going to be saying to dilute it. So we're going to take a small sample of the stock, put it in a container, and add some additional solvent, in this case water, to it. And so one of the things that is really important here is that we understand our equations for dilution, and there's two that we can use. They're basically variations of each other. One is this one that is C1V1 equals C2V2. Where C1 and C2 are the new and the original concentration. C1 is the original, C2 is the new concentration, V1 is the original volume, V2 is the new volume. If we are working with a unit of concentration that's in molarity, we oftentimes will say M1V1 is M2V2, where we've just replaced concentration more specifically here with molarity. Let's go ahead and look at a problem that you could see. We have a 5 milliliter sample of a 0.34 molar solution of NaOH that's added to a beaker. Then 295 milliliters of water is added to the beaker, determine the solution's new concentration. So the first thing we have to do is make sure we understand what information in the problem is important. Obviously, numbers are always important here, and so I'm just going to go ahead and underline those. So when I get ready to look at this, I have 5 mils of a sample that's 0.34 molar. Now those go together, so it's important to keep those together. And we're going to add it to a beaker. So imagine this is our beaker. And we're going to add that 5 milliliters of that 0.34 molar. You're going to be doing this with cheer wine. We're going to have it in there, and then we're going to add in 295 milliliters of water. Now, if this solution was a color, let's say in this case, let's say it's clear in actuality, but let's say it was maybe green. When I add it in there, I'm going to add those 5 mils of 0.34 molar solution, and it's going to be a fairly darker green in color. It's not going to be a large volume. But when I add the water, that's going to dilute my sample and make it less green. It's still going to be green, but it's going to be much lighter in color. So if I'm going to go ahead and begin to solve this problem, I'm going to use M1 V1 as M2 V2, or it can be a C1 V1 C2 V2. The original molarity of my solution is 0.34, and the new volume, the original volume is 5 milliliters. And that is going to equal the new molarity, which is what I'm looking for, the new concentration. So we're going to just leave that in there as an M2. And the new volume. So let's talk about this new volume ideal. The volume is the total amount of solution, which was 5 milliliters, and I put it with 295 milliliters. So what would be the new volume? If you said 300, you are correct. And then what we'll do is solve this problem. You'll say 0.34 times 5 equals M2, which we can treat as X, times 300, and you're going to go ahead and solve it from there. Now, the concentration should definitely be a lot less than the original of the 0.34. And when I do this, you should get 0.0056 molarity. If we're doing sig figs, there's enough 6 after that, so it should really round up to 0.0057. And so that's how you use the dilution equation. Remember, it's a C1 V1 is C2 V2, or M1 V1 is M2 V2. Now, with colorimetry, we often use Beer's law. And Beer's law is what is used to determine the concentration of a solution. A colorimeter is used to determine the absorbance of light. Your phone is going to act as your colorimeter. And what we're going to do is determine, based on your phone, the absorbance of several different samples that you've made. You're going to take the stock solution and you're going to dilute it down and make multiple samples. And then we're going to run the multiple samples. Your phone is going to serve as a light source, and it's going to send light through the sample. Now remember, you are creating your samples in the graduated cylinder in this case. If we are to look down here at our light source, your camera is the light source, so basically it's going to be the flash that is on the back of your camera is going to send light in. And dependent on how concentrated our solution is, some of that light will be absorbed. So in this case, we see a few particles. Your phone is going to compare the light in to the light out, and it's going to create the absorbance value that we're going to use, or we'll get to it. Now imagine if I had a highly concentrated solution. If we think about that, if it's highly concentrated, then our absorbance is going to be a lot less. And so that's for you to keep in mind as you're working with a sample. In this solution, if the samples are more intense in color, or what we would call darker in color, then your absorbance is going to be a lot higher because there's more particles in there. As your absorbance gets, or as your solutions get lighter in color, the absorbance is then going to be a lot less because less of the light is absorbed. With Beer's law, we have this equation where it's A equals the epsilon, the Greek letter BC. And in this case, A is the absorbance. It has no units. E is called the molar epsilon is called the molar absorptivity constant. This is always determined by experiment. So we have to determine it through experiment. So keep that in mind. The units are usually a little funky. They're the units that cause the B and C to cancel out to give absorbance no units. So in this case, if our concentration is in molarity, then E is going to be whatever the units for B are and C, and it's going to be the reciprocal. So it's going to be 1 over Cm times molarity. So that will cause that to cancel out and give absorbance no unit. And C is the concentration, and that can be in molarity, ppms that we're going to use, parts per million, or other units. So once we get the data for each of your known solutions, we're going to begin to create a graph of the samples, and we're going to look at that graph of absorbance. Absorbance is going to be on the Y versus what we call concentration. And so we're going to begin to graph that. And we should begin to get a straight line at some point, and we'll be able to get our Y equals mx plus b equation. And in this case, Y is going to be your absorbance, X is going to be your concentration, and M is going to be your molar absorptivity constants. And after you get your data, we're going to help you with that, because that's a lot to take in. But once you get your data, it'll make more sense. And so remember, the more concentrated the solution, the less light that comes out. The less concentrated or more dilute the solution, the more light comes out. Finally, we want to talk some about units of concentration. Units of concentration can be in molarity, which you're very familiar with. Just remember that's moles of solute over volume. That's total volume of solution. So that would be, as a reminder, the volume of a solute plus the volume of the solvent. Often we use a solid solute, so its volume impact is negligible or has no impact overall. But in this case, you're using volume of a stock solution, so we have to consider that. The next thing you're going to see is parts per million. ppms, which is parts per million. And one of the things that you may be asked to do is convert like a 5 parts per million to molarity. And so in this case, what we would do is use 5 milligrams over 1 liter of solution as an interpretation. And so let's say we had a 5 ppm of NaOH solution. So that would mean I would have 5 milligrams of NaOH over 1 liter of solution. And if I were asked to find that in molarity, I would have to convert my milligrams into moles. So I would convert milligrams to grams first, and then I would have to get moles of NaOH and use its molar mass, which is about 40. And then I would go through and do my math, and that would convert this ppm to molarity. If you have any questions, be sure to let your professor know. Enjoy the lab. It should be a lot of fun.